Hello students, let us continue this session on rational numbers. In our previous session, we had discussed closure property in whole numbers, natural numbers and integers. And I had asked you to think about the closure property under all the operations for the set rational numbers. Let us discuss about the closure property in rational numbers. First, we will discuss under addition. If a and b are any two rational numbers, the sum a plus b equal to c, where c is also a rational number, then the set of rational numbers are said to be closed under addition. Let me consider any of the two rational numbers. Let me consider 1 by 2 and say 3 by 4 as two different rational numbers. To tell you, the set of rational numbers are represented by the letter Q. We all know that the rational number, say 1 by 2, means 1 is divided by 2. Whenever we divide a number by another number, we get quotient. Since the quotient starts with the letter Q, the rational numbers are represented in terms of letter Q. You will study in class 9th onwards that there is another set called as real numbers, and the real numbers are represented using the capital letter R for real numbers. So remember, rational numbers are denoted by capital letter Q. If 1 by 2 and 3 by 4 are rational numbers, their sum (1 by 2 added to 3 by 4, 4 will be the LCM, so 2 plus 3 is 5, 5 upon 4 is also a rational number. For instance, if I take one of them as a negative, so 1 by 2 and negative 3 by 4, they are rational numbers. What will be the sum now? 1 by 2 added to negative 3 by 4. The LCM here again is 4, so 2 minus 3 will become negative 1 upon 4. That is also a rational number. So if you take any two rational numbers, their sum is also a rational number. We say that rational numbers are closed under addition. Let us look at the subtraction. I'll consider the same example 1 by 2 and 3 by 4, and this time I'll subtract 3 by 4 from 1 by 2. Their difference is negative 1 by 4, and it belongs to the same set of rational numbers. If I consider 5 by 6 and 3 by 4 belonging to the same set of rational numbers, their difference is 5 by 6 minus 3 by 4. The LCM of 6 and 4 is 12. So when 12 is the LCM, this has to be multiplied by 2, this has to be multiplied by 3. We get 10 minus 9, which will be positive 1 upon 12. And positive 1 upon 12 is clearly a rational number. If you consider any two rationals, their difference is also a rational number. So we say that rational numbers are closed under subtraction. Let's look into multiplication. The product of any two rational number, is it a rational number? Let's look at an example. 4 by 5 when multiplied with another number 3 by 4, we get 12 upon 20, which can be further simplified and it becomes 3 by 5. If 4 by 5 and 3 by 4, 4 by 5 and 3 by 4 are rational numbers, then their product also is a rational number. Let's look at some other example. Minus 1 by 7 multiplied to minus 3 by 4. What will be the product? It will be negative 1 into negative 3 divided by 7 multiplied to 4. This becomes positive 3 upon 28. It's again a rational number. So the product of any two rational numbers is also a rational number. We say that it's closed under multiplication. Let's have a look at division. Suppose if I consider any two rational numbers, their quotient is also a rational number, provided the second rational number should not be equal to 0. The reason being, the division by 0 is not defined. So if I consider some positive rationals, their quotient, that is 1 by 4, should be divided by 3 by 4. So 1 by 4 is multiplied to the reciprocal 4 by 3 and we get 1 by 3 belonging to the rational numbers. If I consider a negative number divided by another positive number, what will be the quotient? Minus 1 by 4 divided by 3 by 5, this will be minus 1 by 4 multiplied to 5 upon 3. So we get negative 5 by positive 12 belonging to the set of rational numbers. So it is the only set closed under all the four operations. So closure property, if I summarize in terms of natural numbers, these are the operations: addition, subtraction, multiplication and division. Natural numbers are closed under these two operations and they are not closed under multiplication and division. Whole numbers, again they are closed under addition and multiplication. They are not closed under subtraction and division. In set of integers, we have closure property true in these three cases: addition, subtraction, multiplication, not in division. In set of rational numbers, they are closed in all the four operations. This is a summary of closure property in the number systems we studied. This you can make a note of it. This will help you. On moving further, we will take up commutative property, which is also called as commutativity. We will discuss commutative property under two operations: addition and multiplication. The commutative property under addition says that the sum of any two numbers can be interchanged. A plus B, the sum becomes C, and the same sum will be obtained if I reverse the direction of addition. If B is added to A, we get the same sum. Under multiplication, the product of any two numbers can be interchanged. Let us discuss this commutativity in all the sets we learnt. We'll start with the natural numbers. Let me consider two different natural numbers, say 1 and 5 belonging to natural numbers. Then 1 plus 5, will it be equal to 5 plus 1? Yes, they will be equal. So sum of two natural numbers will be commutative. A plus B will be equal to B plus A. Let's look at the product. If 1, 5 belongs to the set of natural numbers, 1 into 5, it will be equal to 5, which is 5 into 1 also. So A into B will be some number which will be equal to B into A. So the order of addition and multiplication can be changed. Let's look at commutativity of whole numbers. If I consider 0 and some other number, then 0 added to 5 is 5, which is same as 5 added to 0. So A plus B will be equal to C, which is equal to B plus A. At the same time, 0 into 5, the product is 0, which will be equal to 5 into 0. So A into B equal to C, which is equal to B into A. So the order of addition and multiplication can be changed in the set of whole numbers also. Let's look at commutativity in integers. If I consider a negative integer and another positive integer belonging to set of integers, the sum -1 added to 5, will it be equal to 5 added to -1? -1 when added to 5, the larger number is 5, the smaller number is -1. Since they are unlike, they have the different sign, we need to do subtraction by taking the sign of the larger number. So the absolute values are subtracted and the sign of the larger number is considered, we get +4. Same is the case here. When 5 is added to -1, it will be 5 minus 1. By taking the sign of the larger number as positive, we get the result as 4. So A plus B will be equal to C. This is equal to B plus A. If I do multiplication, -1 multiplied to 5 will be -5, and 5 when multiplied to -1, this will be -5. So A into B will be equal to C, which is equal to B into A. So in integers also we have the numbers can be interchanged while adding or multiplying. Let's take up rational numbers. Suppose if I consider 3/4 as one of the rational number and 2/3 as another rational number, their sum 3/4 added to 2/3, will it be equal to 2/3 added to 3/4? LCM in both the cases is 12. If 12 is the LCM, this has to be multiplied by 3, it becomes 9. This has to be multiplied by 4, it becomes 8. In this case, 2 to be multiplied by 4, it becomes 8. 3 to be multiplied by 3, it becomes 9. 9 plus 8 is 17. So 17 upon 12. 8 plus 9 is also 17. 17 upon 12, they become equal. So A plus B is equal to C, which is equal to B plus A. The commutative property under addition is verified. Let's look at the multiplication. 3 by 4 multiplied to 2 by 3. 2 by 3 multiplied to 3 by 4. Here, it's very clear that the numerators are multiplied, denominators are multiplied. This 3 can be cancelled out. And 2 one time, 2 times is 4. We get the result as 1 by 2. So the product A into B will be equal to C. This is equal to B into A. Hence, the addition and subtraction of two numbers can be interchanged in the set of rational numbers also. So all these number systems are commutative under addition and multiplication. With this, let's discuss associative property, which is also known as associativity. Here again we have two different properties. Under addition, A plus B plus C will be equal to A plus B plus C. Under multiplication, A into B into C equal to A into B into C. Let us take up example and check the associative property, both this under addition as well as under multiplication. I'll consider a simple example 1, 2, 3 belonging to the set of natural numbers. Let me verify A plus B plus C equal to A plus B plus C. I want you to recall that in Bodmer's rule, we have learned that whatever is in the bracket to be simplified first. So let me consider the left hand side. The left hand side is A plus B plus C. So 1 added to the sum 2 plus 3. Now within the bracket we have 2 added to 3. This becomes 5. 1 plus 5 will become equal to 6. Let me take out the right hand side. In the right hand side we have the sum A plus B to be added to C. So 1 plus 2 to be added to 3. We get 3 added to 3. This is again 6. So we get left hand side equal to right hand side. Hence, the associativity under addition is verified. Let's do the same thing with multiplication. Let me consider the same 1, 2, 3 as the three different numbers of natural numbers. I need to verify A into the product B into C equal to the product A into B into C. Let me take the left hand side. 1 to be multiplied to 2 into 3. So 1 to be multiplied to, this should be 6. 1 times of 6 is 6. In the right hand side, we have 1 into 2 multiplied to 3. 1 into 2 is 2, multiplied to 3, we get 6. So left hand side and right hand side are equal. The same example also holds true for whole numbers. For integers, I'll consider a negative integer, a positive integer, and another positive integer. Let us verify, this is Z. Let us verify the associative property in terms of integers, in the set of integers. So A added to B plus C equal to A plus B added to C. Let's take left hand side. We have negative 3 to be added to the sum 5 plus 7. So negative 3 to be added to the sum becomes 12. When 12 and negative 3 to be added, we do subtraction and we take the sign of the larger absolute value. This will become positive 9. Let's take up the right hand side. In the right hand side, we have minus 3 to be added to 5 and that sum to be added to 7. So here it is 5 minus 3. We have to take the sign of larger absolute value. So we get 2 added to 7. This becomes 9. So left hand side equal to right hand side. So associative property of integers under addition is verified. Let's take the same example, negative 3, 5 and 7 belonging to the set of integers, and verify the associative property in multiplication under multiplication. Left hand side we have negative 3 multiplied to 5 into 7. So negative 3 multiplied to 35. We get negative 105. Let's take up the right hand side. We have negative 3 multiplied to 5. Product is multiplied to 7. This will be minus 15. Multiplied to 7, we get minus 105. So left hand side equal to right hand side. We have verified the associative property under multiplication in the set of integers. In the next session, let's look at the associative property of rational numbers. That's all for today's session. Thank you.